Okay, so now we know a little bit about what a reaction rate is. We know some factors that affect reaction rates. Now let's talk about the reaction rate law. It is a mathematical relationship between the concentration of the reactants and the rate of the reaction. And a couple things here. Let's say we have a general reaction where A and B go to X and the little letters are the coefficients. So then the rate of reaction will be equal to little k, lowercase k, times the concentration of A. And here I've made a mistake. I want to make it very clear, so I'm going to cancel those out. The exponents I'm going to call y, z, and t. So those are lowercase letters there. Zoom in a little bit. And I'm changing these because I want to make it very clear that exponents in the rate law do not have to be and are oftentimes not. So let's say this, exponents in the rate law are unrelated to coefficients in the reaction. And sometimes they turn out to be the same, but the process for finding the exponents in the rate law is entirely unrelated, and it is entirely data-based. So, and you will see that oftentimes they are different, especially in problems in my class, just to make sure that you're using the data, and you will have the data to figure them out. And we'll see what happens in the examples in my lecture here, but sometimes they are the same. Okay, now let's talk about little k. This is lowercase k. And we will, it still stands for constant. We'll see uppercase k in a little bit next time, whichever direction that is. And it is the rate constant. And because little k, these can be exponents, can be any values, the rate constant can have any units. And the units only depend on everything else. So we've seen that rate of reaction is typically in molarity per second, could also be in molarity per hour or molarity per day, could also be in milliliters of gas per minute. So anyway, we'll see some crazy units as we work through this. K, note, lowercase k is a function of temperature. T, capital T, is temperature, but not concentration. Okay. For our class, let me talk about y, z, and t. Y, z, and t, the exponents are typically zero, 1, 2, or half. They can be other values, but typically, I guess the other big one, we probably won't even see 3. We might see 3. Let's write 3 in there as well. And again, they could be other values, as we'll see, but these are the ones we will see in our class. And we'll restrict ourselves. I'm happy to restrict myself right now to exam questions that only have these numbers as answers on exam questions. Now, let's talk about reaction order. Let's say, example, that for a reaction that takes 2 molecules of dinitrogen pentoxide, and when they react, the products are 4 molecules or 4 moles of nitrogen dioxide plus oxygen gas. that you determine the reaction, the experimentally determined rate law, and you found it to be that rate equals K times concentration of N2O5. And there's no 1 here, but of course we don't have to show the 1. And then what we would say is that this experiment, so this reaction is first order with respect to N2O5. And the first order overall. Where the overall part adds up all of the exponents. And so overall is going to be the sum of all orders. And let's suppose we had another reaction, and that reaction took 2. So let me try and think of one I know here. Let's do S2, I want to say O8, 2 minus, aqueous, plus I minus, 3I minus, aqueous, goes to products. And it's okay that I cannot remember the products, but I can only remember the reactants in this because we would determine this using the method of initial rates, which we're about to talk about. But let's suppose that the experimentally determined rate law was rate equals K times concentration of S2O8, 2 minus, times concentration of I minus. And what you can see is the 1 coefficient is the exponent here. The 3 is different for this one. And what we would say is this reaction is first order in peroxodisulfate. Just remember the name of that one. First order in iodide. Reaction is first order in S2O8, 2 minus. And first order in I minus. And second order overall. So those are 2 examples of reaction order, which we will then talk about in future ones. All right, so now how do we determine the rate law? And we'll call it the experimental rate law because that's how we determine it. We'll use the method of initial rates. The method of initial rates says do 2 different experiments with 2 different initial concentrations, and sometimes you'll have to do more experiments, but it'll actually be 2 experiments per exponent, where the only concentration that changes is the one that you're trying to determine the exponent for. Where, let's say this, where only one concentration changes. Because in typical scientific fashion, you want to keep everything constant except the one thing you're trying to learn about. That's what we'll see here. At least in this problem, there's only one exponent that we can determine because there's only one reactant. All right, so you'll get data for these two. You can see that, well, if we were to determine our initial rate by running a tangent right here, and then we might see that the initial rate was equal to 2.2 times 10 to the minus fourth molarity per minute, because we have minutes here and molarity on the y-axis. If you did the same thing here, we would see that the initial rate was 8.9 times 10 to the minus fourth molarity per minute. And again, initial rates are always positive. We're looking at a reactant, so we've divided through by, or we've multiplied by 1 over the coefficient, which is just 1, and put a minus sign in there as well. Anyway, so this is really legit experimental data. You get 2.2 times 10 to the minus 4 for experiment 1. You get 8.9 times 10 to the minus 4 for experiment 2. And the one other thing we need to know is that our rate law has to be rate equals k, little k, times concentration of this compound NH4NCO to the, let's say, x, where x is what we don't know. That's an x up there. I apologize if it's kind of small to see. Okay, so now on to calculations. And the calculations are going to say, and let me write the experimental rate law here. Rate equals k times concentration of NH4NCO to the x. Now, what we're going to do is we're going to quite literally plug into this for experiment 1. We know the rate. It's going to be 2.2 times 10 to the minus 4 equals k, which we don't know. We have the concentration here, which I'll use parentheses now, 0.14 to the x. And let's go ahead and do experiment 2 right below it. 8.9 times 10 to the minus 4. And I should put in my units in there, but I've left them out. I apologize. But we'll put them back in at the end. No, we should put them in now. Molarity per minute. Molarity per minute. Sorry, that's kind of tiny there. Zoom in. And then molarity right here. Now here's the beautiful thing we're about to do. We're going to take these two equations, which are equal to each other, and divide them by each other. What we get then is that, first of all, the units do cancel out, I'm very happy to say. So divide the two reactions, or the two equations, by each other. Divide the two reactions by each other. All right, and what you get then is your units do cancel out. You get 0.247 on the left-hand side. Your k's go away, yay, and you get 0.5 to the x on the right-hand side. And the completely general way to do this, to solve this equation, is now you take the logarithm of both sides, take the logarithm of the whole equation, which is log 0.247 equals log 0.5 to the x. In an exponent, the log comes down in the front, like so. And now we're off screen. There we go. Then to solve this, we're going to actually take the log of 0.247. I'll zoom out a little bit. There we go. 0.247 log minus 0.607 equals x times log of 0.5 minus 0.301. Now divide through. And x equals, well, 0.607 divided by 0.301, 2.02. And somewhat like empirical formula problems, these coefficients have to be small whole numbers or small ratios of whole numbers. My x equals 2. That means that my experimentally determined rate law colon rate equals K times concentration of my reactant squared. That's the method of initial rates, and that is doing it the long, drawn-out log way, and this way always works. It's tedious, it's long, but it always works. Now let's do a second example using ratios of logs. In this reaction of nitric oxide with hydrogen, we've got a couple things going on here. First, we have 3 experiments. And what I will point out to you is that it's important to find, let's see, between experiments 1 and 3, the concentration of NO is constant, while the concentration of H2 changes. And we can see the effect of only the concentration of H2 on the rate, or the initial rate in this case. So we will use experiments 3 and 1 to find the exponent on hydrogen. And let me just write this out. Rate equals K times concentration of NO to the X times concentration of H2 to, well, we'll just call it Y in this case. And zoom in, there we go. So we will use experiments 1 and 3 to find Y. And let's see. Well, this should be interesting. So there are no experiments where the hydrogen concentration stays the same. So we'll deal with that too. All right. So we have a whole nother page to work on this. Good. And let's determine Y first. In order to do that, we will do the same thing we did on the previous page, except I'm going to note that for experiment 3, the concentration of hydrogen is greater. So I'm going to put experiment 3 on top. For experiment 3, using our formula here, rate, which is 0.120 molarity per minute, equals K, which we don't know, times concentration of NO, which is 0.1, to the X, concentration of hydrogen, 0.200, to the Y, and those are both molarities. That's experiment 3. Now right under it, I'm going to put experiment 1. For experiment 1, I have rate equals 0.00600. Molarity per minute equals K. My concentration of my NO is still 0.100. My concentration of my hydrogen is 0.100 to the Y. So now let's work with this. I'm going to divide my 2 again. I see that my K's cancel out. My 0.100 to the X's cancel out. Shoo! And I'm left with, well, my units canceling out, and I'm left with this ratio, 0.012, or sorry, 0.12, good, divided by 0.006 equals 20. Yeah, that's what it says. So 20 equals 2 to the Y. And something doesn't quite seem right there. Ah, yes. So I found an error in my notes. So this should be 0.0120. Something didn't seem right there. And that means this is 0.0120, which means this is 2. Good, because otherwise we weren't going to get a small whole number. All right, fix that, please. I will attempt to update the notes before you get them. Now, 2 to the Y equals 2. Y has to equal 1. So, and this works typically, if it does, by putting the larger numbers on top, and hopefully you can get a nice number there. Now, all right, now we've got Y, and what we'd really like is we'd like hydrogen concentration to be constant. We don't have that, so we're going to have to carry it through, meaning we're going to have to plug it in. We will see that it won't cancel out all nicely like this did last time, but it'll still work. So let's see. I like looking at these experiments, and I'll zoom out. I like experiments 1 and 2 because something doubles, and this triples though, but we'll deal with that. So I'm going to use the data from experiments 1 and 2 to find X. And again, you could pick 1 or 2, you could pick 2 and 3, just as long as the nitrogen oxide, monoxide concentration does change. So let's do 1 and 2. And 2 has it on top, so I'm going to write experiment 2 on top. That's going to be rate for experiment 2 is 0.144 molarity per minute equals K, which we still don't know. And we'll actually determine K this time. And concentration of NO in experiment 2, 0.200 molar. X. I don't know why I'm using these square brackets, but let's stick with it. For experiment 2, 0.300 molar. And we now know that this exponent is a 1. And now we'll do experiment 1, which is 0.00600 molar per minute equals K. And experiment 1, 0.100 molar to the X, 0.100 molar to the 1. They're equal to each other. We can divide them and it doesn't change anything. And what we get now is 0.100 0.144 divided by 0.006, which is 24, equals my k's cancel. I get 2 to the x, and this is just going to be 3. Divide through by 3 on each side. I get 8 equals 2 to the x, which must mean x equals 3. That is a nice whole number. I like it. And my rate law now is rate equals K times concentration of my nitrogen monoxide cubed times concentration of hydrogen, H2, to the first power. And now let's find K. You can find K if you've done your work correctly using any of these, because K is a constant. So I like the numbers in the first one. They're 0.1s. Those are easy numbers for me. I'm going to plug in those numbers and solve for K. I get my rate 0.00600, and here's where keeping your units is important, because I always care about the units of little k. Molarity per minute, I have my concentration of NO from experiment 1, 0.100 molarity cubed, 0.100 molarity to the first power, and now it's K is the only thing I don't know. I will divide my left-hand side by 0.1 to the fourth power to solve for little k. And little k is going to be 0.006 divided by 0.1. I guess I'm just going to do squared squared to the fourth power. And k equals 60. My units. Well, I should have done this out. It's going to be molarity. Well, the molarity cancels, and I have 3 molarities in the bottom. Molarity cubed minutes. And so that's, let's see, so writing it all out, which we will probably be asked to do, rate equals 60, 1 over molarity cubed minutes. Concentration again, square brackets. Nitrogen monoxide to the third power. Hydrogen to the first power. And after all that, we have determined the experimentally determined rate law completely.